In this video, we'll continue our discussion of evaluating a line integral to find work through a conservative vector field. First thing first, I want to talk about this theorem for just a bit, just to point out. So through the examples, and I wanted to work a few before I pointed out, if you go back and look at the problems that you've done, I've always just put a point A to a point B. I never even talked about, in the previous problems, we always talked about the line segment from A to B, or we'd say from point A to B along x squared, or y equals x squared, or whatever. We would say some kind of path, but these have only talked about like A to B. It doesn't even actually tell me which path to take. And that is because, let's take a look at our formula. We have this path C times dr, and we know if the vector field is conservative, then I just take the upper bound and plug it into my potential function and subtract it from the lower bound plugged into my potential function. C never really matters here. B is usually some point, right? B would be like this, E1 plugging into phi, and 1, 0 would be plugging it in. So what this implies is that we have something called path independence. I spelled it right there, independence. Path independence. We could take any path from point A to point B. It could be a straight path. It could be like this. It could go all the way around, and as long as it stays like that, right? I could take any path, right? I could do 1,000 circles, and the work would still be the same in a conservative vector field because this is equal to work, and I know it doesn't matter what the path was. All I'm doing is plugging in my points. That is a bit neat, that we don't have to worry about the path. All right, so we get what's called path independence, meaning the path does not matter, only if it's conservative. So with this problem, the first thing we need to do is show that it's conservative. So we're going to do the partial of n with respect to x. We just have that ln of x that's affected. It's 1 over x. The partial of m with respect to y, though, we have 1 over x, because the y is like a constant, sorry, the 1 over x is like a constant to the y, right? Like 3y would be 3, so yeah, I think you guys have that probably down at this point. That tells me that f is conservative. So we know that f is conservative. I'm going to start writing this now, independent of path. It doesn't matter of what path we take, because our method doesn't even take it into consideration. But we want to think about that because there's going to be some problems that if you can catch it before you do a little bit of work. Okay, so if that's the case, then there exists a phi such that that gives me my f. And we can redefine f as the partial of phi with respect to x, the partial of phi with respect to y, and then that is my vector mn. All right, we can use this to find phi then. That will just be the integral of my phi function derivative with respect to x dx. Right? This is just m dx. And then we put m there. I got x squared plus y over x. Right, and then we get dx. Okay, working this out, we got 1/3 x cubed. Right, and then we have this y over x. If I take that derivative, I'm going to get y, or integral. I get ln of x. And then I got this function of y. X's are positive, or I would need to do that. But they're positive, so I don't need to worry about it. It's 1 to e. And its path, independent path, so I can just assume it's a positive path. All right, so I have phi of that. I like to rewrite it here. Phi of xy equals 1/3 x cubed plus y ln of x plus h of y. This helps me remember what to do next. Then we can take the derivative partial of phi with respect to y. We're going to get ln of x plus h prime of y, and we're going to set that equal, because we know phi with respect to y is the same thing as n. So we can say it's equal to n, And then I'm going to replace that to y squared plus ln of x. What's really nice is those ln of x's, all our other variables should go away at this point. So h of y, h prime of y, is equal to y squared. I can do that integral to h of y then is 1/3 y to the third plus c. So we have phi now, phi of xy is equal to 1/3 x cubed plus y ln of x plus 1/3 y cubed plus c. Now we can find work. Thus, work is the line integral of the dot product of f dr, which is just phi of, and then we have our points. Let me just pull up my notes. It's just going to be phi of E1 minus phi of 1, 0. We're going to plug that into our function. It's not much work at all. It's just plugging it in. Actually, we should probably talk about our logarithms because not a lot of people are great at those. So I get a 1/3 e to the third. And then plugging e, I got 1 in there. Ln of e is just 1. So we got a plus 1. And then plugging in y there, I got a 1/3. The c is going to go away. I'm not even going to deal with it. X is 1 then, so I got 1/3. I get a 0 in the second term and a 0 in the third term. So I just get that minus 1/3. And that is equal to 1/3 e to the third plus 1. It's not bad. So that's the work of that line. Remember, independent of path is that new thing I wanted to really have you see in these videos, but I wanted you to see a few examples to see that we actually never referred to the path at all besides the beginning point and the ending point, which gave us independence of path. There was a note in your notes in the past, maybe that I wrote in there. I can't recall if we put it in there or not, so I'm going to fit it in here. And then we have a few examples that are going to really highlight the independence of path property.